Hi there, class. So in this lecture video, I will go over the practice problems that will prepare you for exam 2, the second midterm of our class. And so in this midterm, we will cover lesson 4B, 5, and 6. All right, so let's start with 4B. Remember, in this lesson, we were learning about bonding and more particularly covalent bonding. In the previous lecture, in 4A, we would learn ionic bonding. So that's not going to be on the second midterm. So starting in the second midterm, we will start with 4B, which is covalent bonding. So in this first problem, it asks us to draw a Lewis structure. Okay, so to draw Lewis structures, there are certain steps you have to go through. So let's go over them. The first step you have to go through is to find out how many valence electrons are there totally in a molecule. So in problem A here, we have Br2. So you go to your periodic table and find where Br is. And Br is on the 17th column, or we call it 7A, meaning it has 7 valence electrons. Okay, so if it has 7 valence electrons, 7 times 2 is 14 valence electrons, right? So then we connect the two atoms together. Each time we connect two atoms together with a line like that, it represents 2 electrons used. So therefore, there's only 12 left. The next step you do is then you give all the electrons, you give enough electrons on the outside atoms. In this case, there's no outside atoms because there's only 2 atoms. So you give electrons until bromine is full of octet, right? So right now it has 2, so that means you need 6 more electrons. 6 on the left-hand side and 6 on the right-hand side bromine. When we do that, notice that both BRs are now full of octet, full of 8 electrons. And now let's finally count, did we use 14 electrons? So we have 1, 2, 3, 4, 5, 6, 7 pairs of electrons. 7 times 2 is 14. So that's exactly the amount of electrons we have. If you have those two criteria met, one is that everything is octet or duet if it's a hydrogen, and 2, if you have the correct amount of electrons, valence electrons totally, then you are good. So we fulfill those 2 points, so that for A is correct. Let's go to B now. B is O2. So again, we go to our periodic table. O2, oxygen is in group 6A. Therefore, it has 6 valence electrons. 6 valence electrons means it has 12 total because there's 2 oxygens. So let's keep that in mind. That it has 12 valence electrons. So we combine them with a simple line. And then we fill the rest with 8 electrons total, so meaning 6 added to each, just like the case in bromine. Now we count. 1, 2, 3, 4, 5, 6, 7. 7 pairs of electrons. Ooh, that's 14, right? So actually we used more than what we have, which is 12. So in fact, this one, maybe we take away 1 pair of electrons. So now let's count again. 1, 2, 3, 4, 5, 6 pairs. 6 times 2 is 12 electrons. Okay. So we have the right amount of electrons totally, but is everybody happy with an octet? No, right? You notice the oxygen on the right only has how many? 1 pair, 2 pair, 3 pairs. So it's only 6 electrons, not yet 8. So how do we make it happy? Notice that we can start sharing electrons if an atom is not yet full with an octet. So it looks over to its partner, the other oxygen, and asks to share that green pair of electron that I've highlighted. So if something is shared, we have to then erase it from as a lone pair, add it as a shared bond, a shared pair of electrons. Okay, so now let's count. So the oxygen on the right has those 3 highlighted pairs, and then the third pair right there makes it a 4th pair, so 8 electrons. The hydrogen on the right has 1 pair, 2 pair, 3 pair, 4 pair also. 8 electrons. Notice if it's shared electrons, we can count it twice, or count it as how many times, or as long as that atom is connected to it. Okay, let's go to C now. We got nitrogen and hydrogen. Okay, so finally, let's find where nitrogen is. Nitrogen's right there, and therefore it has 5 electrons. Hydrogen's right there, so it has 1 electron. So nitrogen has 5, and hydrogen has 1, but remember there's 3 hydrogens, so you have to multiply it by 3 for a total of 3 for hydrogen's sake. And together, 3 plus 5 is 8. So we have 8 valence electrons. In this case, in case C, now we have a lot of atoms, so one of them must be the central atom. The rule is, for symmetry's sake, that's going to be in the atom that gives symmetry to this compound will give it to make it be in the middle. Another way of saying that is the less amount in terms of the element, that atom will be in the center. So in this case, we have 1 nitrogen, so that's going to be in the center, whereas hydrogens, there's a lot of, so it's going to be on the outside. Okay, so we say to ourselves, we have nitrogen in the inside, and we just simply connect it to the 3 hydrogens. It doesn't matter where you draw the hydrogens as long as they are connected to the nitrogen. Now, since we draw the 3 bonds, we have used, therefore, 6 electrons. So there's only 2 electrons left. And since hydrogen can only accommodate 2 electrons, it's already happy. You don't need to add more electrons to it. So the last 2 electrons you can put into the nitrogen in the center. And in fact, when you do that, it gives nitrogen a full octet also. And we also use all 8 electrons. So that Lewis structure is complete. Next, let's go to HCl. So remember what hydrogen is. Hydrogen is 1 electron, and Cl, do you recall where Cl is? Cl is a halogen, so it's 7 electrons, just like that bromine on top. So a total of 8 valence electrons. In this case, there's only 2 atoms, so we don't have to really consider how or who is in the center. We just simply connect the 2 atoms. One connection gives us 2 electrons. So we have 6 electrons left. So I'm going to give it all to chlorine because hydrogen doesn't need it. Again, chlorine is octet, hydrogen is duet, and we use 8 valence electrons totally. This is a complete structure. Next, SO2. Okay, so let's go back to our periodic table. Where is SO2 here? S here, O here. Okay, so they're both in the 6A column, so they both have 6 valence electrons to contribute. So sulfur gives 6 electrons, oxygen gives 6, but there's 2 oxygens, so multiplied by 2, that's 12. And so a total 12 plus 6 is 18 valence electrons. So in this case, we do have more than 2 atoms, so we need to figure out which one is in the center. What do you think? S or O? For the sake of symmetry, sulfur is going to be in the center. Simply put sulfur in the center and connect on either side with the 2 oxygens. Using 2 bonds means we use 4 valence electrons. 2 times 2 is 4. Next, put the electrons on the outside atoms first until they each get 8 total. So oxygen already has 2 on the left, so I'm going to put 6 more. The same thing with oxygen on the right, already has 2, so I'm going to put 6 more. Okay, so that's a total of how many valence we used already. 8 times 8, 8 plus 8 is 16, and we have 18 valence electrons totally. So that means we have 2 left over. The 2 left over we always put in the center. Now, once we put it in the center, we have used all our valence electrons. However, sulfur is not yet happy with a full octet. When you're not happy with the full octet, you start to ask to share. Okay. So it doesn't matter which partner you ask. In this case, there's 2 oxygens. Just take the lone pair from one and make it a bonding pair. Okay, so I'm gonna erase the one on the right just because, and then therefore move it to the center or move it between sulfur and oxygen to make it a double bond. Okay, notice that the oxygen on the right, if you count its valence electron, 1, 2, 3, 4, so 8 valence electrons, and to count the sulfur, 1, 2, 3, 4, also 8 electrons, right? So both sulfur and oxygen have 8 electrons. Just because they're sharing, it doesn't mean it has less. So therefore, this is a correct, proper Lewis structure. Okay, lastly, F here is COF2. So let's go to our periodic table again. C right there, so 4 electrons. O, 6 electrons. F, 7 electrons. Okay, so C is 4, O is 6, F is 7, but there's 2 of that. So that's 14. 14 plus 10 is 24. So 24 valence electrons. So we have a lot of different atoms in this case. So which one is in our which one will be in the center? So notice that there's 1 carbon and 1 oxygen. So either one could be in the center. So the last rule, if it comes to a tie like that, to break it, the less electronegative atom is in the center. So carbon and oxygen electronegativity, the hungriness for electrons increases on the periodic table from left to right and from bottom up. So carbon, oxygen on the periodic table, carbon is more to the left of oxygen, right? So it's the least electronegative between the two, or the less electronegative between the two. So carbon is going to be in the center. If carbon's in the center, you simply connect the outside atoms with it. So we have oxygens, fluorine on both sides. Again, it doesn't really matter where you draw the atoms, as long as they're connected to the carbon in the center. All right, now we just keep on giving electrons until we have an octet for all the atoms on the outside. That means 6 electrons each. Okay, so 6, 8. 8 times 3 is 24. That's all the electrons we have. But carbon is not yet happy. So again, what do we do when carbon or the central atom is not octet? We have to borrow. Okay, so where do we think we want to borrow? Do you think we want to borrow from a very electronegative fluorine, or not so, less electronegative oxygen, right? It turns out oxygen is less electronegative, so it's less hungry. So it's okay to borrow from oxygen rather than from the fluorine. Okay, so that's the correct Lewis structure. So that's as complicated as it gets in this class in terms of Lewis structures. Now let's move on to nomenclature of these covalent compounds. So it asks us to write the formula for each compound. These are covalent compounds, so we have to know the way it is named. Remember, in covalent compound, you tell the reader exactly how many atoms of each element you have, not based on charge or anything, because it is covalent, it's not ionic. Okay, so in this case, diselenium decafluoride. Okay, so we just have to know the prefix, di meaning 2, right? And selenium, so we have to go find where selenium is. Where is selenium? Selenium is right there, so it's element 34, so its abbreviation is Se. Fluoride, we probably know because it's a common one. We keep on using that. So that's F, element 9. We would say selenium is Se. Di means there's 2 of them. Fluoride is F, and deca means there's how many? 10. So this formula is Se2F10. Next, carbon monoxide. Okay, notice that there's no prefix in front of the first element. When there's no prefix in the front of the first element, that means there's only one of it. We don't say monocarbon, we just say carbon. But the second element, oxygen, has only one also, but because it's a second element, we need to be more clear about it, so we say mono. So therefore, this compound is just CnO, carbon monoxide. Next, tetraphosphorus trisulfide. Okay, phosphorus is P, phosphorus. Tetra means how many? 4. Sulfur, sulfide is sulfur. And how many is tri? Tri is 3. All right, so that's it for number 2. Number 3, it says to write the name for each covalent compound. Okay, so this is the opposite of 2. So we know that the first one is chlorine. So we just say its name, chlorine. And the second element there, O2, mean there's 2 oxygens. So we say chlorine dioxide. And then in B, now there's 2 chlorines and 1 oxygen. So now we say, because there's 2 chlorines, we have to say dichlorine. And then the second element is 1 oxygen, but we have to say, because it's the second element, we have to say monoxide. So instead, we just write 1 O, right? Mono, you can write monoxide like that. But there's a little kink there because there's 2 oxygens right next to two O's right next to each other in the spelling. You often will see it as monoxide like that. We don't say monoxide, we just kind of get rid of 1 oxygen and get rid of one O and just say monoxide, dichlorine monoxide. Okay, C, again, there's 2 chlorines, so we say dichlorine. And then there's 7. How do you say 7? Hepta oxide. I think it's pronounced heptoxide. Yeah, so it's dichlorine heptoxide. You drop the A in that one also. So that's a special case for oxygen. You just drop it, the last vowel of the prefix. Okay, next, number 4, solubility. So H2O, which is water, is a polar molecule, and octane is a non-polar molecule with a lower density. Explain what happens if a large amount of octane is spilled in a lake. Okay, so this is the idea of solubility. Like will dissolve like. Polar molecule will dissolve or mix well, is another way of saying dissolve, in polar molecules. Non-polar molecules will not mix well in polar molecule. So in this case we have here is water, which is polar, and octane, which is non-polar. So the first thing is that we know they're not going to mix well. They're going to be separated into 2 substances. We are also given the fact that octane has a lower density. So going back to our lesson on density, the less dense material will always be on top. The higher density material will be on the bottom, right? That's why when you have octane spill in the lake, the octane would just be on the surface of the lake because it doesn't dissolve into the lake and it's less dense, so it rises to the top. So that's what the answer would be. All right, the last one here, at the end of this chapter, we also touch base on this one type of molecular compound. And not all acids and bases are indeed molecular compounds. There can be ionic acids too, and bases, ionic bases too. But we just want to kind of touch base on this idea. So that's why we kind of add it at the end of the lecture here. So in this problem, it says to look up the pH of the following household items, list them, and determine if the items are acidic or basic. Knowing that pH 7 is neutral, anything below pH 7 we consider acid, above 7 we consider basic. So the farther away from 7, the more acidic or the more basic it is. Okay, so if you just do simple Google search or some kind of internet search, or even if you actually did like textbook search, you can also do that. But the simplest is to go on the internet and just search it. So A is milk, and you don't have to have the exact same pH as I do, but it should be around the ballpark of it. So I have here milk to be pH of 6.6. Okay, so if it's pH 6.6, we call that acidic. Okay, and we call that acid. Hot sauce, I got a pH of 4.6, so that's also acidic. Window cleaner, when I typed up window cleaner, nothing shows up, so I just typed in Windex, which is a type of window cleaner, a brand name. And when I did that, it did show me a pH of 9. And then there were other window cleaners, a pH 13. So regardless, window cleaner is basic. Now, the baking soda, when I searched, it was a pH of 8. So that's basic also. Bleach had a very high pH when I searched. It was pH of 12. So that's definitely basic. Apple juice, on the other hand, had a pH of 4. So that's acidic. Okay, so just know that definition of what is an acid and base, and know some qualities of acids and bases. Okay, that's round out our lecture 4B. Now let's go to unit 5. And it's all about nuclear chemistry. So chemistry that's happening inside the nucleus of the atom, which is a very rare type of chemistry. So let's take a look at the first problem here. Radioactive isotopes like radium-226, which occurs naturally in soils, decay and produces radon-222, a radioactive gas that can further decay into polonium-218. If this process occurs beneath your house, high concentrations of the radon gas may accumulate indoors, posing a health risk. And why it is a health risk is because inhalation of this gas into your lungs can lead to the development of things like lung cancer. Okay, so this is just some side information about how this can be applied to our everyday experience, and hopefully it's not, because that's not safe. So the first question here is, the radioactive decay of radium-226 is what type of radioactive decay? If you know that the product is radon-222, write its nuclear equation. Okay, so nuclear equation starts with the isotope on the left-hand side. That's kind of decay. So radium, if you look at the periodic table, is down here, and radon is over here. Okay, so find your periodic table and find that information. So radium is Ra-226 is its mass number, so I write that on the top. And its atomic number is 88. That's important to write, even though it is redundant. It decays until we get, what do we get? We get radon, which is Rn-226. And radon-226, radon has element number 86 protons. Okay, so remember, it has to be balanced. So there has to be something, 226 plus what? Whoa, why is it 226? 222. My bad. Radon-222 is its mass number. Okay, so 222 plus what is equal to 226 plus 4, right? So we know it has an addition of 4 mass units. And then 86 plus 2 in the bottom is 88. So we know that this element also has 2 protons. And so what is that? That's helium nucleus, aka the alpha particle. Okay. Next, the radioactive decay of radon-222 is what type of radioactive decay? If you know the product is polonium-218. Okay, so same thing. We start out with radon now, 222, and we know that was also 86 on the bottom. It decays into polonium, which is PO. So let's find what PO is. Polonium is right there. Polonium is element 84, and you have mass number of 218 for this isotope. So again, for mass-wise, 218 plus what equals 222? That's plus 4, right? And the bottom, 84 plus 2 becomes 86. So that is also an alpha particle. And lastly, if radon 222 decay was outside the body, would it cause the same harm? Why or why not? Okay. So this radioactive isotope is dangerous to us, like the problem says earlier, because when we inhale it into our lungs, it causes damage because it releases the alpha particle, and then it damages DNA that way, right? But the question here is saying, if it's on the outside of your body, would it be harmful? In fact, it won't, because alpha particles are so big, when it collides, it basically collides with the air in the atmosphere, or with your skin, or with your clothes. It doesn't even go into your organs, and therefore cannot damage your DNA. Again, because the alpha particle that's being released is very large. So in fact, if this was indeed the case, radon is much more dangerous in your body and not very dangerous outside your body, because it doesn't penetrate your body. Okay, so that's the reason for C. Next, number 2, yttrium-90 is injected into a joint to relieve the pain caused by arthritis. It is a beta emitter. Okay, this time it's telling us what kind of decay is going on, and then write its nuclear equation. Okay, so yttrium, we looked that up. So where is yttrium? Yttrium is right there. So Y, element number 39, yttrium-90 has a mass number of 90. It will decay, and this time I'm telling you it's a beta emitter. So that means a beta particle is symbolized with an E and -1 charge on the bottom and 0 mass on the top. Okay, so let's do the addition of that. So we take it to the bottom number first. 39 is on the left. So what plus -1 is equal to 39? 40, right? So 40 plus -1 equals 39. And then on the tops, what adds with 0 equals 90? It would just still be 90. So the last thing you have to do is find what element is number 40, because that number in the bottom just tells you the number of protons and therefore the number of the element, right? So 40 is right there, zirconium. So we just say then this is the product of that beta decay. Number 3. So the rest of these problems now talk about an idea of half-life, something that is a quality of radioactive decay, meaning that a certain time passes where half of the radiation still exists. And so that time is constant. For every time that passes, another half is cut off. So number 3, a sample of technetium 99M is an ideal radioisotope for scanning organs because it has a half-life of 6 hours and is a pure gamma emitter. Suppose that 140 milligrams were prepared in the morning at 6 a.m. About how many milligrams of technetium 99M is left by midnight that same day? Okay, so we have to really figure out how much time has passed, because we know that each 6 hours is one half-life. So if we start at 6 a.m., 6 hours pass would be what? Noon? Another 6 hours that pass is what? 6 p.m. But then it says it's left at midnight. Okay, so that's another 6 hours that pass to give us midnight. Okay, so how many 6 hours passed? 1, 2, 3, 6 hours. So therefore 3 half-lives have passed, right? So we suppose we start with 140. So here is 140 milligram. You divide up by half. In the first half-life is 70 milligrams. The second half-life, again, you divide by 2 again, gives us 35 milligram. And then you divide it the third time. What's 35 divided by 2? Oh, yes, 17 and a half. So the answer is 17.5 milligrams would be left at midnight. Okay. Number 4, in a 1 microgram sample of carbon from a live tree, the activity of carbon-14 is 6.4 microcuries. If researchers determine that 1 microgram, okay, so it has to be the same amount for this problem to work, so that's why it says 1 microgram, of charcoal from a prehistoric cave painting has an activity of 0.80 microcurie. What is the age of the painting, knowing that carbon-14 has a half-life of 5,730 years? Okay, so review my lecture on carbon dating to really understand how this works. So I'm just going to show you how the math works in this video. So we know that a normal activity for like fresh carbon-14 is 6.4 microcuries, but in this one it has only 0.8. So we're basically figuring out how many half-lives has occurred for it to reach 0.8, starting at 6.4. So the best way to do that is saying to yourself, okay, I start out 6.4 microcuries, because remember, this can be in terms of mass of the radioisotopes or in terms of the radioactivity measurement. So in this case, it's microcuries. So 6.4, if you divide it by 2, so I'm going to say that's the first half-life. What's 6.4 divided by 2? 6.4 divided by 2 would give us 3.2 microcuries. All right, so that's not yet 0.8, so I'm going to do the second half-life. Divide that by 2. That's 1.6 microcuries. Again, that's not 0.8, so I'm going to do a third half-life. Oh, there we go, 0.8 microcuries. So it turns out it needed 3 half-lives, right? So 3 half-lives, and each half-life is 5,730 years. So you simply say 3 times 5,730 years. So 3 times 5,730 is 17,190 years. That's how old that piece of charcoal is, based on its half-life and its leftover remaining radioactivity. All right, so that was unit 5, radioactivity, radionuclear chemistry. Now let's go to our last unit covered in this exam, which is organic chemistry. And in this one, we're going to have to learn how to draw bonds between carbons and carbon and hydrogens. The first one, the first question here is about skeletal structure. Another way of calling that is called a bond line structure. In a bond line structures, every time you see a zigzag line, a segment, that means 2 carbons are connected. If a line segment is connected to another element that is not carbon, then you have to write it out, like that bromine in that first case there. And then every carbon has to have 4 bonds or 4 lines to it. So if it doesn't, that means the remaining lines are 2 hydrogens. So hydrogens are just simply ignored. Okay. So in the first question, it says to redraw the following structures with all the bonds and atoms clearly shown, meaning the hydrogens that we ignore, we have to draw them out. Okay, so the first one here, I'm going to go ahead and highlight my carbon. So 1 here, 2 here, and 3 here. You see all that's the zigzag, all that segment. At the end of each segment is a carbon, except when it is written out, then it's not a carbon. Okay, so I'm going to go ahead and say carbon here, and carbon here. Starting from the left, that left carbon is connected to 1 bromine, and then that carbon is connected to this carbon and to that carbon. So the carbon on the right has a connection doubly to 1 oxygen and then to 1 oxygen again, singly this time. And just to complete this side out, that oxygen is connected to a hydrogen. Now, this structure is not yet complete because you have to look at all the carbons to see if there's any hidden hydrogens. So let's first start with the one on the right. The carbon on the right has already 4 bonds, so it's already happy, octet. let's go to the second carbon. This carbon here was this carbon here. So notice that it has only 2 bonds to it, so therefore how many hydrogens are left? There are 2 more hydrogens left. Okay, how about the last carbon here on our left-hand side? This carbon, again, it has 2 bonds already, so therefore 2 more hydrogens. Okay, so that's the structure of that molecule fully drawn out. Okay, let's do B now. B is a big molecule, so I'm going to need some space. I'm going to fortunately have to erase. So let's just draw all the carbons out first. Okay, so this is 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6 carbons. Now off of the 5th carbon, there's 2 more carbons, right? So I'm just going to write it. And you can draw, you don't have to draw the one on top going up. You can just draw it going down. But if you want, you can draw it going up also. It doesn't really matter. But I'm going to do one up and one down just so it doesn't confuse you. Okay, now off of carbon number 3, there's 1 again, 2, 3, 4, 5 carbons in a ring. So this is carbon number 3. So it's 1, 2, 3, 4, 5 connected back to the first carbon. All right, so we've drawn all out carbons out. I'm going to draw hydrogens this time in black so there's a distinction. Okay, let's go from the left-hand side here. This left-hand carbon, top left-hand here has only 1 carbon connection, so therefore how many more bonds? 3 more hydrogens, right? Going across, carbon number 2 has 2, so therefore 2 more hydrogens. Carbon number 3 has 3 bonds already, so 1 more hydrogen. Carbon number 4 has 2 bonds, so 2 more hydrogens. Carbon number 5, 4 bonds, so no more hydrogens. Carbon number 6 has only 1 bond, so 3 hydrogens. And the other 2 carbons connected to carbon number 5, the same thing. Now let's go to the ring. The ring that's connected, the carbon on the ring that's connected to carbon number 3 has how many bonds already? 3, right? So it has only 1 more bond to hydrogen. Let's go around the circle. Notice each carbon around the circle has only 2 connections. So therefore, each carbon has 2 hydrogens. Okay. See how ugly this structure is? And kind of like too busy, so it doesn't really help us if we take a look at this molecule. So that's why we use the bond line and skeletal structure. It makes the compound much more simple, and therefore features of it can stand out much more easily. The carbon-hydrogen bond aren't that interesting, so that's why we kind of ignore them and when we draw the skeletal structure. Okay, let's do that again for our last molecule here. Notice that this one here has a ring that is composed of 6 carbons. So I'm going to go ahead and draw those in. 6 carbons in. And carbon number 3 is also connected to an oxygen and a carbon. Carbon number 4 is connected to an oxygen and a hydrogen. Carbon number 5 is connected to another oxygen and another carbon. Carbon number 1 and 2 actually has a double bond. Carbon number 3 and 4 has a double bond. Carbon number 5 and 6 also has a double bond. All right, let's go to carbon number 1. How many bonds does it have right now? It has 3 bonds, so therefore 1 more hydrogen. Carbon number 2 has 3 bonds, therefore 1 more hydrogen. Carbon number 3, 4 bonds, so no more hydrogens. Very good. Carbon number 4, 4 bonds, so no more hydrogens. Carbon number 3, 4 bonds, so no more hydrogens. And did I say 3? I meant 5. Lastly, the carbon number 6, 3 bonds, so 1 more hydrogen. Now let's go to the ones on the side here. On the right-hand side, the carbon that's connected to that oxygen, only one bond, so 3 more hydrogens. So same with this one. So there you have it, all of the hydrogens drawn in. All right, our last problem here is about functional groups. In organic chemistry, there are millions and millions of atoms, molecules out there, right? So in order to kind of group them together to know their patterns in reactivity, because if they have the similar kind of atoms and the arrangement of atoms, they behave in a similar way. So we have grouped them in what is known as functional groups. So let's go ahead and label all the functional groups in these molecules. So these are all real molecules, drug molecules, or even preservatives. I think BPA is a preservative, right? But the other ones are all drugs, medicine. Okay, so let's look at the first one here is cortisone. So I'm going to zoom in. So again, review my lecture to know what are the functional groups and how to recognize them. But so we're going to try to do that here quickly. Okay, so starting from the top up here, an OH group by itself like that, we call that an alcohol. And then this group right here is a carbonyl, but attached to the carbonyls are just carbons. So what do we call that? We call that ketone. This OH here is also an alcohol. Oh, again, we have here a carbonyl, a CO double bond with 2 carbons attached to that carbon of the carbonyl. So we call this a ketone. Right here, we have 2 carbon bonds. We have 2 carbons doubly bonded. We call this a alkene. And again, that CO double bond with carbons on the side, we call that a ketone. Next, let's go to tamoxifen. So this is an estrogen modulator. So we see here, we have, I'm gonna just circle all of them this time and call all of that aromatics. So the blue is aromatics. We have here an alkene. Ooh, we have an oxygen. And on both sides of the oxygens are just carbons. So that's an ether. And lastly, we have a nitrogen and call that amine. Okay, next. Fentanyl. Okay, this is the opioid that's killing people, but that's just a molecule. Let's go ahead and take a look at this molecule. Again, we have some aromatics. We have the same amine group we saw earlier. But notice when a nitrogen is connected to a carbonyl, we don't call it an amine anymore. We call it a amide. Okay, so that's a special group also. BPA, actually not a preservative, I thought it was. It says here it's used to make polycarbonate plastic. I guess that's the warning you see sometimes when you buy things that says BPA free. So it is a carcinogen. Try to avoid that, but some stuff will have it. Okay, so we have here aromatics again. So I'm just gonna circle that, color coordinate it with blue for aromatic and alcohol for the OH. Remember, alcohol is also known, that OH is also known as a hydroxyl group. So you see that, but we call it an alcohol. Okay, ascorbic acid, aka vitamin C. Okay, so it has a lot of oxygen. So let's do those first. We have that OH, that OH, that OH, and this OH. So they're all, so I'm going to circle in red, they're all alcohols. So we have something else that's different in this molecule though. We have this one, a carbonyl this time bonded to an oxygen. A carbonyl bonded to an oxygen. So we call this an ester. And lastly, that's just our friendly alkene, carbon-carbon double bond. And then our last molecule of the day here is vanillin. This is what is the essence of vanilla. So what is vanillin? It has an aromatic group. It has an alcohol group. An aromatic and alcohol together sometimes is known as a phenol group, but we don't have to know that in this class. Okay, what are the other things here? Remember this? Oxygen with carbons on both sides. We call that ether. And then lastly, we have a carbonyl, but this carbonyl has a hydrogen on one side. So that has a special name. That's called the aldehyde. Okay, so that's the functional groups. So it's kind of fun. I think it's fun to kind of look at the molecules and know what kind of functional groups they have in there. So I think you just need a lot of practice in order to identify the function groups in this lesson. All right, so that ends our lecture for this week. So hopefully you get to review some ionic compounds, some nuclear chemistry, and some organic chemistry to get you ready for midterm number 2 at the end of the week. And of course, always come see me in my office hours if you would like to ask any questions to kind of clarify any concepts before the midterm.